Okay, my friends, so now to the second part of the study, the one where we got a big p-value from. Now remember the hypotheses, they're the same as they were before. Secondhand smoke has no negative effect is the null. Secondhand smoke does have a negative effect. That's the research. Okay, now a big p-value, bigger than 5%, means we are back in this null. A big p-value bigger than 5% means that we're going to believe the null this time. Formally, this is called failing to reject the null. I prefer believe the null hypothesis, and here's why. Remember, the null hypothesis carries this sampling distribution. The research hypothesis would be the reduced lung function parameter. But in this part of the study, after 3 hours, the data landed somewhere more like here. Now again, that data could be on either curve. It could be on the blue curve or it could be on the yellow curve, but it's more likely to be on the blue curve because of where the data is positioned. The blue curve is higher than the yellow curve at that point. Now, if you get a large p-value, the common response and the correct response is to say nothing changed. Believe the null. In this case, lung function parameter is at baseline. But it's possible that it has changed, even though you concluded that it didn't. And that's called a type 2 error. Let's talk about that more now. Okay, my friends, type 2 error, and I bet you those among you who have already looked at the project for this week have probably realized this is also a false negative, more colloquially. I think I said that right. Like I said, medical, judicial, statistical, all means the same thing. It means that something did change, but you missed it. You're never going to know for 100% certainty if you make either of these kinds of errors. But the only way you potentially could make this error is if you get a big p-value. And you act appropriately. If you get a big p-value, you're going to believe the null hypothesis. You're going to say, well, nothing changed. There's always the chance that it could. Now, here's where it gets interesting. Remember in the last video, we said that the probability for a type 1 error is 5% if we are operating at 95% confidence. Okay, that's true. Whatever confidence we're operating at, it's going to be whatever's left to get to 100%. As a matter of fact, there's a Greek letter for this, lowercase alpha. It's kind of like one of those Darwin fish you see on the back of people's cars, but that's a lowercase alpha. You can calculate what that lowercase alpha is because you know the confidence you're operating at, and you know the chance of that weird little outliery region. Type 2 errors are more squirrely. And I think we're going to look at this later on in the course in your second exam. I can't tell you right now for that study what the chance of a type 2 error would be on that big p-value conclusion. Beta is the language or the Greek letter that is used to stand for a type 2 error. But it's a little bit, and there's not enough time in this course to really get into the mathematics of this. The type 2 error probability depends on the location of that alternative hypothesis sampling distribution, that yellow curve that we saw before. Depending on where that thing is going to impact the size of the type 2 error. So all we can say for certain is type 1, if you can make a type 1 error, is going to be 5% at 95% confidence. Beta's not quite as neat. But don't get too far in the weeds right there. The thing to remember about type 2 errors, false negatives, they can only happen if you get a big p-value. That's it. Okay, I think it's time to wrap this day up with kind of an overview. This week was a lot of stuff without a lot of math, so it might feel a little bit ethereal. Let's wrap up what we're doing this week with last couple slides, and then next week we actually get into calculating some of these p-values and these test statistics. I'm stoked. But for right now, I'll wrap up.